Finally, we want to define line integrals, which are also called sometimes path integrals. Integrals, same thing. And there are, in fact, two different kinds of line integrals. They stem from exactly the same thing, but eventually they have different interpretations in terms of the physics behind them. So we're going to start with line integrals of scalar functions. So here's the setup. F of xy is a scalar function. And everything we do is going to very easily generalize to f of xyz. So just for simplicity, I'm going to write f of xy. But everything generalizes straightforward to f of xyz. So what does it mean, a scalar function? It means that for every point xy, we get a scalar, right? It's a function from R2 to R, okay? And the other piece of data is a curve. Gamma is a curve with some parametrization, and I'm done struggling with that word, with parametrization, R of t equals x of t, y of t. Okay, so since I'm doing f of xy, I'm going to take a planar curve. And again, everything generalizes if you throw in the z. Works just as well. Okay, so f on gamma, f is defined in some region, gamma is contained in that region, and f on gamma is given by f of x of t, y of t. Right? We discussed compositions like this many times, like when we did the chain rule and when we discussed the intermediate value theorem and so on. Right? Everybody good? Okay. So we want to define, let's define the integral of f over gamma. That's what we want to define, and that's going to be called a line integral. Okay? So I first want to, there are two motivations for doing this. One comes from geometry and the other from physics. Let's start from the physics. Physics motivation. So suppose you have, suppose gamma. So in mathematics, gamma is just a curve. In physics, it's going to be something that you can really hold. So the curve is going to be a wire. Okay, gamma is a wire. And you can take this in various directions. You can go in the direction of mass, or you can go in the direction of charge. Let's suppose we go in the direction of charge. So suppose that we know that the wire has some charge density given by fxy. So it's a planar wire. It sits here on the plane, and it's charged. Okay, it's electrically charged, but at every point, the charge at that point is given by fxy. Okay, and we want to know the total charge of the entire wire. Okay, so how do we do it? If this was a constant function, then the total charge of the wire would be just the length of the wire times the charge. Okay, but if it varies, then we can't just do the length of the wire times the charge, because this varies. It's not a constant. So what do we do? And tell me if you recognize the idea. Here's the wire. We say, okay, let's take a little segment here. Okay, let's just look at this tiny little segment in red. But it's too tiny for us to work with, so let's draw it a bit bigger here. Here's the little red segment. Now this little red segment corresponds to, let's use the arc length parameter. Remember the little s arc length parameter? So this corresponds to si minus 1, and this corresponds to si. Okay, so here's the little segment, si minus 1 and si. What is the length of the little segment?
Si minus si.
Exactly. The length of this little segment is precisely delta si, which is si minus 1. In the parameter, right? Because the parameter si is precisely the length of the curve up to the point si, right? And si minus 1 is precisely the length of the curve up to this point. So the length of this little segment is precisely si minus 1. Is that clear? Okay. So what is the charge of this little segment of the wire? Well, f varies, but if the little segment is small enough, we can choose a point here, any point in between, and say, okay, f is continuous. Usually we assume our functions are continuous, so we'll just take the value at this point, x of s, y of s, x of s, y of s. There's a value at this point, right? And the total charge of this little segment is approximately the value of the charge at this point times the length of the segment. Do you agree? That's an approximation. Of course, the value here and here and here are slightly different, but very slightly because it's a very small segment. So that's an approximation. Do you agree? So the total charge of the wire is approximately sigma I equals 1 to n, where that covers all the little segments, the value of f at these intermediate points, x of s, let's call them, let's just assume we take this point, doesn't matter. We can call them f of x, si, y of si, okay, or any point in between. You can call it s bar, call the point in between s bar, and then it would be s bar I. Doesn't matter. Okay, you can either take this point or any point in between, right? Times the length of the segment. Do you agree that this approximates the total charge of the wire? Okay. As we make the segment smaller and smaller, refine the partition, what would this approach? As we refine the partition, it would approach the integral from s equals 0 to s equals L, from 0 to L, right? These are the endpoint values of the parametrization. Let's write it L, right? Of f of xy times ds. ds is this arc length variable. Do you agree? Okay, so this is how we do integrals all the time. You should start feeling that, well, it's just doing the same thing again and again and again, each time with a different meaning, and that's precisely what it is. Okay? Now, this is not something we can actually work with. This is not something really accurate. I should leave the x of s, y of s, because s is the variable. X of s, y of s, ds. The reason this is not practical enough is because we don't know what this s variable really is. The curve is given, gamma is given, let's go one board back, gamma was given with some concrete parametrization. We want to work with this. This is something we know. These are actual functions, cosine, sine. This is something we can actually put our hands on and calculate, whereas that thing, the integral from 0 to L of f of x of s, y of s, ds, is something abstract, okay? But we can translate, and the translation is nice and elegant and enables calculations. So let's rewrite this again using that translation. So we define, so that was the motivation, but here's the formal definition. The integral of a function f over a curve gamma ds, this is just notation. You can't do anything with this. This is shorthand notation for what we just wrote, the integral from 0 to L, f of x of s, y of s, ds. And this is still something that you can't really work with because you don't know what s is. But we can do a change of variables here. This is a regular integral with, this is an integral of a one variable function, right? The integral is over s. The variable is s, right? The fact that this expression comes from a two variable function, but for a concrete f, you plug in s for x, s for y, right? And you get an expression with s's. Do you agree? Like cosine s. If f of xy was x squared plus y squared, you would get cosine squared plus sine squared, or whatever. Okay? So how do we do change of variables? Let's do change of variables just like we do it in Calc 1. Instead of s, we're going to replace s by t. Okay, we want to change variables to t. And how do we do that? What is ds going to be? It's going to be s prime of t dt, right? This is how we do change of variables, right? Everybody with me? But we know what s prime of t is. S prime of t, so you have to recall this, was none other than r prime of t. And this we saw in the previous clip when we discussed this arc length parameter and how it relates to any old parameter. Okay, remember this? So what we get is the integral. When s is 0, t is going to be a. When s is L, t is going to be b. These are the original bounds of the parametrization by the parameter t. And then f of x of s, y of s is going to become f of x of t, y of t. And ds is going to become r prime of t, dt. Clear? And this is something we can actually calculate. This is something, we know what x of t and y of t are. We know what f is. All of this is something we can actually calculate. We'll do examples in a second. Okay? So this is an intermediate step. You don't have to write this again and again. This is just how the theory becomes concrete. This is the actual thing we calculate. This is the line integral of a scalar function. Okay? So let me rewrite this integral of gamma f ds. This is the notation that we use, and this is the actual thing we calculate. And like other important formulas, let's put it in a box. To highlight it and to give it some respect. Clear? Let's do an example. Okay. Examples. So let's suppose that we have the curve r of t equals cosine t, sine of t, t. Remember what this curve was? It's not a circle. Look, there's another coordinate here. Right, this was the helix, the slinky. Remember that? Everybody? And you're going to say now, wait, we just did this for functions of two variables. But everything works for functions of 3 variables as well. Let's do it for a function of 3 variables. Okay? So this is going to be the curve. This is the helix. T is going to range between 0 and 2 pi. So this is the helix. And let's take the function f of x, y, z is going to be the function x squared plus y squared plus z squared. Okay? So suppose I have this slinky, and I charged it, and the charge at any given point in space is given by this, which is just the square of the distance from the origin. Okay? And I want to know, what is the charge of the entire slinky? Okay, well, this is just one round of the slinky, right? Because we're only going as far as 2 pi. Okay, so what's it going to be? Well, I need to calculate r prime of t. R prime of t is the root of x of t squared plus y of t squared plus z of t squared. Do you agree? And cosine squared plus sine squared is 1. Oh, sorry. Do you agree?
No.
Complete nonsense. Complete nonsense. Ah, oh, shame on me. I just took the coordinates of r, right? I want the length of the coordinate, the length of r prime, right? So I need the derivative. Let's write it. X prime of t squared plus y prime of t squared plus z prime of t squared. So x prime is minus sine of t squared plus cosine of t squared plus 1 squared. And then I need the root of this. Now do you agree? So sine squared plus cosine squared is 1, plus 1 is 1. So what I get here is just root 2. This is an easy example, I admit, but we'll do more sophisticated examples later. So this is r prime of t, and therefore the integral of f over gamma ds, physically the charge of the entire wire gamma, this one round of the slinky, is, I have to calculate f on the parametrization. So f is x squared plus y squared plus z squared, and now I have to calculate it on the parametrization, right? Let's write once again the formula. Let's write it now for functions of, for the function of 3 variables. So it's going to be the integral from 0 to 2 pi, the integral from 0 to 2 pi of f of x of t, y of t, z of t, times r prime of t, dt. This is what I want to calculate. So what is f of x of t, y of t, z of t? I have to plug in x of t, y of t, z of t into the formula for f. So I get cosine squared of t plus sine squared of t plus 1 squared. And then all of this I have to multiply by r prime of t, which I just calculate, root 2, and then do dt.
Why not t squared?
Why is it 1?
Hmm?
It's not t squared?
T. Thank you. Good? Do you see that it becomes a single variable calculus in the variable t, in the parameter, right? It's something we can actually calculate. And in fact, it's not even hard. Cosine squared plus sine squared is 1, right? So what do we get? We get root 2 can just hop out. And then we get the integral from 0 to 2 pi of 1 plus t squared dt. And this is a very elementary integral, right? So it's root 2. The antiderivative is t plus t to the power 3 over 3, evaluated between 0 and 2 pi. Do you agree? And now comes the hard part. So Standing on my knees is hard. So when I plug in 2 pi, so what do I get? Root 2 times 2 pi plus 2 pi cubed is 8 pi cubed over 3. And that's basically the answer. Good? Everybody? Okay, so this is an example. I want to go back to the theory just for a minute and tell you the geometric interpretation of a line integral. Okay, so let's do that. So we're in the same setup. So we have a scalar function and we have a parametric curve. And I want to show you a geometric interpretation of the exact same thing, the line integral. So here goes. So here is gamma. Gamma is a curve. The geometric interpretation is going to really be something we can relate to when it's done in 2 variables. So wait, 2 variables. Why did I just draw the x, y, z coordinate system? Right, the graph is going to live up here, right? Okay. So suppose I have some curve down here. Let's draw the curve in blue. Here's a curve. This is x and y. And this is the bad blue. Where's the good blue? Here's a curve in the xy plane. Suppose it looks something like this. This is gamma. So do you see that this is a curve that's on the floor? Okay, it's a curve in x and y. Gamma equals r of t, which is x of t, y of t. Okay? I don't want to write gamma equals. Gamma is given by r of t, which is x of t, y of t. It lies here on the floor. Good? This corresponds to maybe t equals a, and this point corresponds to t equals b. So this is one part of the data for this. There's a curve. Also, there's a function, right? fxy. Where does fxy live? Where does the graph of fxy live? Right. fxy lives somewhere up here. So this is the graph of fxy. Do you agree? Okay. The value of f, remember what we want to do. We want to calculate the integral of f on the curve, right? That's what we wanted to define. So if I look, maybe let's take a different color, at the values, I want to move this so we have more space here. So let's write t equals b here. And this is the curve. So the value of f only for points on the curve is going to look maybe something like this. Clear? This is the value at this point. This is the value at this point. This is the value at this point. For any point on the curve, we have some value of f on the curve. Do you agree? Okay? And let's make it more interesting. It looks like it's just another copy of the curve down there, but that's not necessarily the case. The case can be maybe something like this. Okay, the graph of f, it depends on what the graph of f looks like. Okay? Now, so this orange picture is f of x of t, y of t. Okay, the orange is not that good anymore, but that's what it is. Do you agree? Okay. Now, suppose I want to know, so here's the geometry here. I want to know what is the integral of what is the integral of a function in general? For a single variable function, it was the area under the graph, right? For a two-variable function, it was the volume under the graph. Remember? Now what we have is a two-variable function, but we're really looking at it not over an area, but rather over a line, right? So the integral of f of x of t, y of t, the integral of the function, not over a domain in xy, but rather over a line, is going to be the area under the graph. Okay? So what do I mean the area under the graph? I'm going to do another sort of connect the dots thingy here. Under each point lives above some point down here. And what you should be picturing now is a fence. You should be picturing like a fence here, and the bottom of the fence is the curve in the xy plane. The top of the fence is not constant, but it's the values of f over this curve, and the area of the fence, the amount of wood you need in order to construct this fence, the area under the graph is precisely, well, let's say what it is precisely. It's this little segment here corresponds to a delta SI, a little segment, and I'm multiplying this delta SI by the value of f at some intermediate point. So if I take this almost rectangular little thingish, the area of this thing is going to be almost f at x of s, y of s, or si, times delta si. That's the area of this rectangle here. Do you agree? Just this one. Just this part of the fence. Just this wooden, how would you call it? Exactly. Okay? And what would be the area of the entire fence? You'd need to add all these up, right? Add all these little wooden bars. We know how to add things up. Put a sigma. Right? This is the approximation, because the height of the fence is not constant. Right? It's given by this function. Here, for example, the height varies. Do you see that? And here the height varies. Right? But this is an approximation, and as we take the limit, as we refine the partition, what we get is the integral from 0 to L in the S parameter of f of x of s, y of s, ds. And again, this can be translated to the dt in the exact same manner that we did before. Okay? So the geometric motivation or interpretation of a line integral is area under the graph of fxy over gamma. And it's an area, it's not a volume. Because we're not looking over a domain, we're looking over a line. Is this clear? Is the idea here clear? Can you picture it? Can you see that it's very similar to Calc 1? Okay, good? Okay, doing this in 3 dimensions is a bit trickier, right? Because we can't draw. We can't draw f of x, y, z. Okay, but the idea is similar. Okay, so this is the geometry behind this notion of... by the way, one remark. Suppose our function was the constant function 1. Suppose we were building a fence which is precisely the same height all along gamma. We can do that, right? I can take a few of these and we can build a fence which is precisely the same height. Where am I? There we go. Clear? What would we get for this integral? What would f be? 1. So we would get the integral of the function 1. The area under the graph of the function 1 above the curve, which is what? It would be simply the length of the curve. Clear? So remark, if f is just a constant function 1, then we get the line integral becomes simply the length of the curve. Do you agree? Questions? Yes.
How do we find when, for example, on the homework, we're usually not given which one is the lower and upper bound? How do we know which one to make A and B?
Okay, so when you're given a parametrization, the starting point of examples or of exercises could be different. Okay, you could be given a curve where you have to find the parametrization, and then you can choose. Or you can given a curve that already comes with a given parametrization. Okay, and the convention is, unless it's stated explicitly otherwise, the convention is that the starting point and the ending point of the parametrization are the direction in which the parameter goes up. Okay, the parameter becomes bigger. So if you have from 0 to 2 pi, you think of 0 as the starting point and 2 pi as the ending point. Okay, in terms of line integrals of scalar functions, it's not going to make much of a difference because you don't want it to depend on which direction of the parameter you took, right? You want the area under the graph, so you would just define if you take the parameter going from 2 pi to 0, you put a minus and that's it, right? We're going to see in the second kind of line integrals that we're going to discuss, not for scalar functions, but for functions which we already mentioned are called fields, functions that their values are vectors, the direction is going to play an important role. It's going to be different if you, the result of the integral is going to be different if you go like this along the curve or if you go like this along the curve. Okay? More questions? Okay, so coming up next, line integrals of vector fields rather than scalar functions. That's coming up next.